In this lesson, we will discuss valence bond theory and hybridization. These theories attempt to explain how covalent bonds are formed in the shapes that we observe. Let's begin by reviewing the learning goals for this lesson. After this lesson, you will be able to identify the hybridization based on the electron pair geometry of a given atom. You will be able to describe the types of bonds and atomic orbitals used to make them for a given molecule. You will be able to apply the model of hybridization to molecules described by multiple resonance structures. And certainly this final goal will be the most challenging, but we can do it. You can think about this as similar to when I asked you to predict the bond lengths in benzene, and we had to consider the fact that benzene is represented by two equivalent resonance structures before predicting those bond lengths. So we'll apply that same idea to assigning hybridization. Let's get started. We'll begin by reflecting. Please respond to both of these questions. Write down your answers. What information what is required, what information must be included in a Lewis structure, and what information might be missing from a Lewis structure? Again, pause and respond to these questions in writing. Well, all atoms and valence electrons must be included in a Lewis structure. I'll list some more common answers that I hear to this question. In addition to all atoms and valence electrons, students often say that the types of bonds can be inferred from a Lewis structure. For example, you can see double versus single bonds, and you might infer the presence of sigma versus pi bonds if you recall those, and if you don't recall that, you very soon will. Now, what information might be missing from a Lewis structure? Well, Lewis structures don't have to be drawn with the correct bond angles or the correct shapes. For example, if you were asked to draw the Lewis structure of ammonia, this is certainly a correct Lewis structure. It shows all the bonding and non-bonding electrons and all the atoms. Of course, it's not in the right shape, but that's not required for drawing a complete Lewis structure. And even the true information about the types of bonds may be missing from a Lewis structure, right? So maybe even the true nature of the types of bonds. And I'll call that bond order, single, double, triple bond. So maybe even the true bond order is missing. So related to this point that we made, that the types of bonds can be seen in a Lewis structure. If we just draw a single Lewis structure for benzene, we might think that there would be alternating long and short bonds between the carbon atoms. But that's not correct because we need to account for the other Lewis structure that describes this molecule, the resonance structure. And then once we account for both structures, then we realize why all of those carbon-carbon bonds have the same length. So really the only information that must be included in a Lewis structure are the atoms and the valence electrons. And then if we want to consider the types of bonds, are they double, are they single? What is the shape? What are the bond angles of the molecule? Well, then we need to think carefully about, for example, whether or not the molecule may be represented by resonance structures, or how many electron domains are about a given atom, and then redraw in the proper shape. So drawing Lewis structures is not something that we do in 5 seconds and then move on from. We actually have to put some thought into the structure once we've just represented all the atoms and valence electrons. Let's review how carbon makes its bonds. So carbon bonds with its what? Valence electrons. And electrons exist in Orbitals, so defined regions of space with given energy. What orbitals exist in the valence shell? Okay, so if carbon makes bonds with its valence electrons, we need to think about the orbitals that those valence electrons exist in. So, what orbitals exist in the valence shell of a ground state carbon atom? Draw a representation of each of these orbitals in 3D space. So, draw a picture of the orbitals. Go ahead, pause, and do that. Carbon has atomic number 6 protons, so a neutral atom has 6 electrons. The electron configuration is written here. The valence shell, the highest energy shell for carbon, is shell 2. There are 4 total electrons in carbon's valence shell. From the periodic table, you can glean all of this information. Carbon is in row 2, thus its valence shell will be shell 2. Also, carbon is in group 4A. So we remember without drawing the electron configuration that carbon will have 4 valence electrons. Orbitals are described with quantum numbers. Quick review. Quantum number n, the principal quantum number, describes the energy level or shell that the orbital is located in. Practically, this tells us how far away from the nucleus on average an electron in that orbital is, as well as what the energy of the electron is. Bigger N means further away from the nucleus and higher energy. L, the orbital quantum number, tells us the shape of the orbital. Recall that when L equals 0, the orbital will have a spherical shape, and we call that an s orbital. When L equals 1, the orbital will have a peanut or dumbbell shape, and we call that a p orbital. All p orbitals have a nodal plane at a 90-degree angle from the axis aligned with the orbital. The third quantum number that we'll consider for drawing these orbitals is m sub L. M sub L will depend on the value of L, and m sub L will tell us the orientation of the orbital in space. For example, the p orbital that I drew here is oriented with what I will arbitrarily call the y-axis, but we could also have a p orbital aligned with, say, the x-axis. And whether or not an orbital is aligned with the y-axis versus the x-axis is going to depend on this value of m sub L. If you need more of a review, please see the quantum mechanics lesson. And now we're going to apply these ideas quickly to the valence shell orbitals for carbon. Because remember, those are going to be making the bonds. All right, valence electrons are the highest energy electrons, and they do the bonding. Carbon's valence shell is shell 2 with principal quantum number 2. When principal quantum number is 2, there are 2 possible values of the orbital quantum number, which, if you remember, goes from 0 to n minus 1. So for n equals 2, L could equal 0 or 1, which is equivalent to n equals 1. Now, the value of m sub L, the magnetic quantum number, which represents the orientation in space of each orbital, depends on the value of L. When L equals 0, m sub L can only equal 0. Its possible values are negative L, 0, so by integers, negative L through 0 to positive L. So when L equals 0, your only option is just 0. When L equals 1, however, the possible values of L are negative 1, 0, and 1. Okay, so that means we have 4 possible orbitals here. Let's draw them out. So when n equals 2, L equals 0, m sub L equals 0. This is the 2s orbital. These quantum numbers describe the 2s orbital. It is s because L equals 0. If this is a little bit unfamiliar, please review the quantum mechanics lecture. Now, when n equals 2, L could equal 1, and m sub L could equal negative 1. We'll call this the 2py orbital. meaning that this orbital will be aligned on the y-axis. That designation is arbitrary. In other words, I am making a decision that m sub l equals -1 will be the 2py. It doesn't particularly matter. It just matters that all three of these p orbitals that I'm about to describe to you are oriented at a 90-degree angle from one another, as represented by the different values of m sub l. Right? They're all going to be p orbitals because when l equals 1, the orbital shape is a p orbital. It's a peanut or dumbbell. But these different values of m sub l, these just tell us the different orientations in space. And please review the quantum mechanics review lesson if you need to see this in a little bit more detail. Now, when n equals 2 and l equals 1, again, it'll be a p orbital because l equals 1, m sub l, the orientation, could correspond to quantum number 0. We will call this the 2px orbital, where the p orbital is aligned along the x-axis. It's still a p orbital, it's still a dumbbell, it still will have this nodal plane at a 90-degree angle from the orbital axis. And then finally, when n equals 2 and l equals 1, there is one more option for the p orbital. The p orbital might have a magnetic quantum number of +1, and in that case, what results is the 2pz orbital, which will be aligned along the z-axis. In carbon's valence shell, there is the 2s orbital and then 3 degenerate p orbitals. There are 3 p orbitals because, again, when L equals 1, when the orbital quantum number that describes the shape of the orbital is 1, there are 3 possibilities for the orientation of that orbital. That orbital can be oriented on the y-axis, the x-axis, or the z-axis, depending on the value of the magnetic quantum number. But all 3 of these p orbitals have the same energy. That's what's meant by degenerate. These 3 orbitals have the same energy, and they're oriented at a 90-degree angle from one another. We're going to revisit this picture and think about how these orbitals make the bonds that we observe carbon making. First, let's draw Lewis structures in the proper 3D orientation for each of these molecules. Please also include approximate bond angles. I've drawn 3D representations of all 3 of these molecules here. Take a look and compare to what you came up with. Quickly, in ethane, each of the carbon atoms has 4 total electron domains, thus a tetrahedral electron pair geometry, which corresponds to 109.5-degree bond angles. In ethene, each of these carbon atoms is bonded to 3 total domains, corresponding to trigonal planar electron pair geometry, which corresponds with 120-degree bond angles. Recall, the electron pair domains are oriented as to minimize repulsions, being as far apart in space as possible. Finally, ethine has 2 carbons, each with 2 total domains, corresponding to linear electron pair geometry and 180-degree bond angles. Now that we refreshed our memory with the molecular shapes of each of these 3 hydrocarbons, can we rationalize the bond angles and the shapes of these molecules given the orbitals in carbon's valence shell? Given these orbitals that we took, 10 minutes to draw out. So given these orbitals, which I'll draw again, can we rationalize these shapes? What do you think? Well, we have the s orbital that's spherical, and then we have the 3 degenerate p orbitals at 90-degree angles from one another. Who sees 90-degree angles here? No one. So, in short, no, these shapes do not make sense based on the orientation of carbon's valence orbitals. But what does that mean? Well, that means some new model will be required to explain the bonding in these molecules. Let's discuss this new model now. This model is the model of hybridization, which is part of valence bond theory. Like you, like us, chemists were unable to explain the geometries of molecules based on the shapes of the atomic orbitals. Thus, as they were sitting around without cell phones, etc., chemists came up with an idea of hybridization. And hybridization of atomic orbitals explains very well the shapes of molecules. However, later, chemists realized that hybridization of orbitals is kind of an absurd idea and does not occur. So why are we learning it? Well, we are learning it because this model makes excellent predictions. So because it's good at making predictions, we're going to use it. It's fine. If you continue in chemistry, you'll learn more sophisticated models later. But for right now, this is the model we're going to use. Excellent. What is hybridization? Well, who's having a panic attack from general chemistry? Well, stop it. Do not panic. You don't have to panic. I'm going to tell you a secret, and this secret will calm all your fears here. So hybridization is the same as electron geometry, and electron geometry is the same as hybridization. Remember, hybridization is a model that explains geometry. Thus, the two things are correlated to one another. When an atom has tetrahedral electron pair geometry, like the two carbons in ethane, those atoms have sp3 hybridization. When atoms have trigonal planar electron pair geometry, like the two carbons in ethane, those atoms have sp2 hybridization. When two atoms have linear electron pair geometry, like the two atoms in ethine, those atoms have sp hybridization. So I ask you, can you assign the electron pair geometry of an atom? Yes, you can. You've been doing this for a while. You can do it. And if you can't do it right now, you're going to go back, review the last lesson, and then you'll be able to. And so because you can do that, you can assign electron pair geometry, you can also assign hybridization. Remember, hybridization is a model that explains geometry. So this is always true. Here are your answers. That said, I want you to understand what hybridization is and what the model is. However, to get most questions right, all you have to know is what I've circled in purple. You can do it. I believe in you. Let's move on. Here is a summary of the relationship between hybridization and VSEPR, valence shell electron pair repulsion geometries. I will walk you through this table and then we will discuss each hybridization in detail. SP hybridization corresponds to linear VSEPR geometry, SP2 trigonal planar, SP3 tetrahedral. These hybridizations explain the observed bond angles for each of these geometries. Now, what we have this picture of here, this picture, for example, for the SP hybrid orbitals, this represents two hybrid orbitals, two SP orbitals overlaid in space. I'm about to show you that SP orbitals look like this. Whoa. And for an SP hybridized atom, it has two of those orbitals. The nucleus is around here somewhere. And so those orbitals, when they're overlaid on one another, look something like this. And then we just ignore the small lobes in these pictures. So that means that this picture represents 3 overlaid sp2 orbitals. And this picture represents how many? Yeah, you've guessed it, 4 overlaid sp3 orbitals. All right, let's talk about all these hybridizations. First of all, what the heck is hybridization? Well, hybridization just means that two atomic orbitals are combined. They are equations, right? We model them with equations, so we can add them and subtract them. So you can take these equations, add them up, and you're going to get two new combinations, two new orbitals. So some chemists did some math, and I'll refrain from jokes after this one about them not having cell phones and social media. But chemists did some math, and they realized when they took the two equations that represented the 2s and one of the two p orbitals, they took them, they combined those math equations to make two new equations, and which represents two new orbitals. Those orbitals that popped out, so we have two sp orbitals. The orbitals that popped out are at a 180-degree angle from one another when they are overlaid, just like I mentioned on the previous slide. So here's one of them, here's the other one of them. We ignore the little lobes, and this picture I drew looks just like this one. Cool. So that's the entire deal. When you add up the math equations that represent the s and p orbital, you form two new orbitals that are oriented with a 180-degree angle. They're oriented in a line. And that is excellent because that could explain how an atom could use those orbitals. Let's imagine we have the carbon for acetylene in there, or one of the carbons for acetylene. You could imagine how it could bond with a hydrogen here, bond with another carbon, that's sp hybridized, and they could bond with another hydrogen. Yeah, look at those 180-degree bond angles. Awesome. Chemists use math to explain what's going on. Now, as I said, not quite, because it turns out that this model is not true, but it's very, very predictive. And so we're going to learn it, and we're going to use it, and we're going to make predictions from it, and we're going to get everything right, because it's a pretty decent model, even though it's not true. I'll point out one more thing before we leave this slide. Not all of the atomic orbitals were used to make the hybrid orbitals. So these two p orbitals, they're just still there after hybridization. So I'm going to refer to these as leftover p orbitals. They're still there and able to make bonds. And we can even draw them in. They're going to be at 90-degree angles to these sp orbitals. So I'm going to draw them in for this carbon here. So it has a p orbital in the plane of the page, and it's going to have another p orbital going in and out of the page. And why not? Let's draw them for both of these carbons for ethyne. Cool. All right, and the carbons will do something else with those bonds, which we'll talk about, or those orbitals, which we'll talk about in a minute. Now that we solved the mystery for sp hybridization, let's write that somewhere. sp, linear. Let's solve the mystery for sp2 hybridization. To generate sp2 hybrid orbitals, the 2s and then two of the 2p orbitals are mixed together. When you mix, when three orbitals are mixed, right? Okay, so we have three orbitals coming together. Three new orbitals result. The total number of orbitals is conserved. Then we can overlay all three of those sp2 orbitals, and we can see, ignoring the little lobes, that there is a 120-degree bond angle between each of those orbitals, and they all lie in the same plane, and that explains trigonal planar geometry. That explains how the carbons in ethylene can make three bonds in the same plane with 120-degree bond angles. I'm going to write out the same diagram that I had drawn on the previous slide. This time the 2s and then two of the 2p's are mixed together. And so we're going to end up with three sp2 orbitals and then one leftover p. I'll point out one more thing before we leave this slide. sp2 means that, so there's an implied 1 here. It means that one s orbital and two p orbitals were combined or were hybridized to make the three new orbitals. One more hybridization to go. What do you think happens for this one? Yes, all four of the valence orbitals for carbon, or whatever atom you were talking about, are combined. So all four atomic orbitals, the s and all three p orbitals, are combined to make four hybrid orbitals, which we call sp3. They're one part s and 3 part p. In other words, 25% s and 75% p. And when they are overlaid, as we can see down here, and again, we're ignoring the little lobes. When they're overlaid, there is a 109.5 degree bond angle, or angle between those orbitals. So you can imagine if this is a carbon atom and it uses these orbitals to bind with, say, the hydrogens, and then this is methane. This explains the shape of methane, right? Methane is tetrahedral. It does have this shape. So hybridization is a very appealing model because it explains the observed VSEPR geometries for molecules. Let's summarize. Pause and fill in this chart. For 4 total electron domains and tetrahedral geometry, the hybridization of the atom will be sp3. This corresponds to 4 sp3 orbitals with 0 leftover p orbitals. That is because all 4 orbitals combine to make 4 hybrid orbitals, to make the 4 bonds that are arranged in that tetrahedral fashion with 109.5 degree bond angles. For 3 total electron domains and trigonal planar electron pair geometry, the hybridization of the atom is sp2. One of the s orbitals and 2 of the p orbitals combine to make 3 hybrid orbitals, which we call sp2, because they are 1 part s and 2 parts p. There is 1 leftover p orbital that was not hybridized. Finally, for 2 electron pair domains and linear electron domain geometry, the atom will be sp hybridized. One of the s orbitals and one of the p orbitals combine to make 2 sp orbitals, and then there will be 2 leftover p orbitals. What's the point of this discussion? Well, let's think about what the hybridized orbitals do. They are holding the electron domains, right? They're giving the electron domains their shape. That is the entire point. So the hybridized orbitals will make sigma bonds. Don't worry if you don't remember what that exactly means. Just 1 second and we're going to talk about it. The hybrid orbitals make sigma bonds or hold lone pairs. Basically, they hold the electron domains. Now, what do these leftover p orbitals do that we've highlighted in yellow? Well, they will either make a pi bond, so make a double bonding interaction. And again, we're going to go over pi bonds in just a moment. Or they will be empty. Before we move on, just a quick note. sp3 hybridized orbitals, as I mentioned, are 25% s and 75% p. sp2 orbitals are 33% s and 67% p. sp orbitals are 50% s and 50% p. So we can say that the sp hybrid orbital has more s character, right? It's 50% s compared to 33 for an sp2 or 25 for an sp3 orbital. It has more s character than sp2 and sp3 hybrid orbitals. Because it is more like an s orbital, and s orbitals are lower energy than p orbitals for multi-electron systems. sp orbitals are lower energy than sp2 and sp3 orbitals. All right, that's an important side note, important point to make before we move on. On the right side here, I have included those pictures of the overlaid orbitals, and I'm going to walk you through them for just a moment before we move on. We can see the 4 hybrid orbitals for sp3 hybridized atoms here overlaid, making this tetrahedral shape. For sp2 hybridized atom, we can see the 3 sp2 orbitals in that all coplanar with 120-degree bond angles between each other. And then what else do we see? Well, we see this leftover p orbital here right there, and it's in a plane perpendicular to the hybrid orbitals. Let's go ahead and write that down. So the leftover p orbital is at a 90-degree angle to the hybrid orbitals. Finally, for the sp2 hybrid, we see the 2 sp2 orbitals with a 180-degree bond angle from one another. We've already seen that. What I more want to point out right now is that those leftover p orbitals, both of them, they're at 90-degree angles from the hybrid orbitals, just as before for the sp2. But this time you have 2 of them, 2 leftover p orbitals. Now that we have these orbitals pointed in the right directions to explain the VSEPR geometries, what do we do with them? How do they make bonds? Well, they overlap. Let's discuss the different types of bonds that they make when they overlap. Sigma bonds are made from hybrid orbitals. So the sp, sp2, or sp3 orbitals will make sigma bonds. Sigma bonds are characterized by head-to-head overlap. This means that orbitals overlap along the bond axis. Because of that, there will be a cylindrical symmetry of electron density about the internuclear axis, and this defines a sigma bond. That was a lot of talking, so let's take an actual look at what a sigma bond looks like and how it is formed. I will imagine that we are bringing together 2 sp3 orbitals. Perhaps they are making the sigma bond in ethane. Valence bond theory states that 2 orbitals overlap, and they overlap by coming together in space. That is what I mean by these 2 arrows. They are overlapping along what will become the bond axis. We can draw their overlap like this, or we can show those 2 big lobes combining to make a new big lobe. Either way, we've shown a sigma orbital, a sigma bonding interaction. A few notes. We've brought together the big lobes of the sp3 orbitals, not the small lobes, because there is more overlap between the orbitals if we bring together the big lobes. So the resulting sigma orbital, the sigma bond, will be stronger if there's more overlap between the orbitals that make it. You can also see that we've brought together the big lobes in phase, meaning they have the same shading. Because sp3 orbitals are derived from p orbitals, they do have this node here, and phase does change shaded to unshaded across the node. So when we bring together the 2 orbitals, we do bring them together with their big lobes both shaded in phase. Why would we do that? Well, recall that Our model for orbitals is that they are waves. We represent them by wave functions. If we're going to add together two wave functions, we want to add them together in phase so that they will constructively interfere. Otherwise, they're going to destructively interfere and cancel each other out. So we're going to add the plus lobe with the plus lobe and the minus lobe with the minus lobe. They will constructively interfere. Ah, look at that, a new wave. Okay, so that's what I mean by in phase. These two waves constructively overlap to make a new wave rather than cancel each other out. And that's what's shown here. So the shaded lobes constructively overlap. Again, we have this head-to-head overlap that makes the sigma interaction rather than a pi interaction, right? So if we brought those two orbitals together like this, that would be a side-to-side interaction. And you're not going to have very good overlap. You would have maybe decent overlap with the big lobes, but the little lobes, can't reach. They can't overlap. It's not going to work out very well. So this does not happen for hybrid orbitals. So those are sigma bonds. We can also have pi bonds, and pi bonds are characterized not by head-to-head overlap, but by side-to-side overlap. Because of the side-to-side overlap, pi orbitals have electron density above and below the internuclear axis, the bond axis, and that is what makes them pi bonds. That is in contrast to the cylindrical density around the bond axis that is seen for sigma orbitals, for sigma bonds. Not the case for pi bonds. For pi bonds, you will have a node on the internuclear axis. Let's show a pi bond being made from two p orbitals. We're going to imagine bringing them together in space, side to side. We bring them together in phase, as I mentioned before, such that the shaded lobe of one orbital interacts with the shaded lobe of the other orbital. The unshaded of one orbital interacts with the unshaded of the other orbital. They constructively interfere. We can draw a pi bond or a pi orbital like this, or we might actually show the overlap between the two lobes and draw a little hamburger. Either drawing is okay. And you can see the bond axis, the internuclear axis. For the pi orbital, you have electron density above the bond axis, below the bond axis, but there is a node on the bond axis, which is derived from the nodal plane that exists from p orbitals. It is at a 90-degree angle to the orbital axis. So there's a node on the bond axis, so there is no electron density on the bond axis. This fact makes pi bonding interactions generally weaker than sigma bonding interactions, which have electron density on the happy place for the electron, the bond axis, close to the nuclei. Not the case for the pi orbital, pi bond. You have a node on the bond axis, which contains the nuclei. Let's take a moment and revisit our theme here. Chemistry is all about electrons. As we've discussed, electrons go to the lowest energy orbital unless they are forced to do otherwise, so unless they're promoted by light or something else. So based on what you've learned so far, what are the lowest energy places for an electron? We can add a few bullet points to our list. We've already learned that low shell number corresponds to lower energy. We know that for multi-electron systems, s orbitals are lower energy than p orbitals, which have a node on the nucleus. Related to this phenomenon, for hybrid orbitals, sp orbitals are lower energy than sp2 or lower energy than sp3. More s character means lower energy. And finally, sigma bonds are lower energy than pi bonding interactions. Pi bonding interactions are made from p orbitals, which again have a node on the internuclear axis. Let's pause and take a moment and answer this question. Are all CH bonds the same? I wonder. I would like for you to identify the shortest CH bond in this molecule. If you think that all of the CH bonds have the same length, awesome, answer same. Then explain your answer. Please try this, take a break, and then come back and rejoin me. No, all CH bonds are not the same. The shortest CH bond in this molecule is this one. Now we had a few choices. We could choose between a CH bond between an sp carbon atom and hydrogen, or we could have chosen a CH bond between an sp2 carbon and hydrogen. Finally, we could have chosen between many possibilities a CH bond between an sp3 carbon and hydrogen. The sp carbon makes the shortest bond to hydrogen because the sp orbital has the most s character and is the lowest energy orbital among these hybrid orbitals. Let's try our hands at drawing pictures of the bonding interactions between atoms. Let's consider the bonding in ethylene. Okay, I used a common name. I've been calling ethylene ethane tonight. That is the systematic name. So I slipped up. Ethylene and ethene are the same. We're going to describe the bonding in ethylene. We're going to draw a complete Lewis structure, label each bond with the type of bond it is, and this should be sigma versus pi, and then from what atomic orbitals it is made. Draw a picture of the orbital interactions for each bond. Typically, students have no idea what I'm asking here, so pause. If we were in class, I would pause now and I would have you answer the question. Just whatever you think I mean, draw it. Last chance. So the Lewis structure for ethene, C2H4, looks like this. Each of these carbon atoms are sp2 hybridized. They have trigonal planar electron pair geometry, 3 total domains of electrons around them both. This, of course, means they have 3 hybrid orbitals with which they will hold the different domains of electrons, making them 120 degrees apart, and then 1 leftover p orbital. These CH bonds, all 4 of them, will be made from an sp2 orbital on carbon and the 1 s orbital on hydrogen. The carbon-carbon bonding interaction consists of 1 sigma bond and 1 pi bond. The first bond is always a sigma bond. The sigma bond is between the sp2 orbital on one carbon and the sp2 orbital on the other carbon. And the pi bond is between the p orbitals that are left over, that are unhybridized, on both of those carbons. Recall our very important table that we made together. Hybrid orbitals make sigma bonds and hold lone pairs. Leftover p orbitals make pi bonds, or they will be empty. Now that we've described the bonding interactions for each bond, let's draw a cartoon diagram. That will be very, very fun. So we have each of our carbon atoms. Let's start with the hybrid orbitals. And each of those atoms are making sigma bonds with their hybrid orbitals. So each carbon bonds to the neighboring carbon and is going to bond to a hydrogen atom, to that 1s orbital from hydrogen. This is not the world's most perfect picture, but we can see the 120-degree bond angles representing this is trigonal planar. And now we have one more interaction to draw, and that's the pi interaction. Now, since I have the sigma interaction is actually in the plane of the paper. The pi interaction should be coming in and out of the plane of the paper, but that's a little bit hard to draw. So here are the p orbitals for both of those carbons, and they're overlapping above the internuclear axis. We can draw that if we want, and below the internuclear axis, just not on it. So this represents one pi bond. And it's easier it would have been easier if we had drawn it with the sigma bonds actually coming in and out of the page, and then we could have shown the p orbitals in the plane. If you have a model, you can make it and get a sense of what I mean. Okay, but these are the same. All right, those are my ugly pictures. Let's look at a lovely picture from your textbook. So this is showing the same thing. So each of these single bonds is made from the hybrid orbitals, and then the double bonding interaction, the pi interaction, that is made from the leftover p orbitals. How do you solve problems like this where you're asked to describe the bonding? Well, I would suggest that you identify the hybridization of all the atoms, and then you list the available orbitals for bonding and go from there. The single bonds will be sigma bonds made from hybrid orbitals, and pi bonds will be formed from p orbitals. Let's try another practice problem. Let's describe the bonding in acetylene. Now you really need to pause because I have given you an example. So let's pause and make sure that you can reproduce this idea. Oh yes, I'm using lots of confusing nomenclature tonight. Acetylene is the common name for ethine. I must have slipped into some bad habits when I wrote these last slides. Here's the Lewis structure. So both of the carbons, they're sp hybridized, which means that they'll have two sp orbitals and two leftover p orbitals. Sp hybridization corresponds to linear electron pair geometry. You gotta live, learn, love this table. The CH bonds are between the sp hybrid orbital on carbon and the 1s orbital on hydrogen. To describe the triple bond between the two carbons, we would consider one sigma bond and two pi interactions. The sigma bonds are formed using the hybrid orbitals. The pi bonds are formed with the leftover p orbitals. So I will arbitrarily say that px for the first carbon and px for the other carbon combined, and then let's say py for one carbon and py of the other carbon. Orientation doesn't matter as long as the p orbital is making the bond overlap. Okay, let's draw out the beautiful picture. So here's our sigma bond made from the sp orbitals, and I'm just showing the big lobe of the sp orbitals. That's okay. Here's another sp orbital. It's making a bond to hydrogen. It's 1s orbital. So I don't think I labeled the sigma interactions between the carbons and the hydrogen in this example. So let's just label all the interactions. So sorry about that. Finally, we need those two pi interactions. So we'll have one pi bond formed in the plane of the page where there's overlap above and below the internuclear axis. So that is one single pi interaction. The other pi interaction will happen perpendicular to this one at a 90-degree angle, perpendicular. There we go. Okay, we've drawn the bonding, shown the bonding for acetylene. We can see there are two perpendicular pi bonds. Just as you're getting the hang of it, I'm going to throw you a curveball. Let's consider the molecular ion nitrate. Draw a complete Lewis structure. Consider all resonance structures. Assign the hybridizations of all atoms. Give it a try. Nitrate is described by three equivalent resonance structures. The actual electronic structure of nitrate is a composite. It is an equal blend of these three structures. We can recognize that nitrate can be described by resonance structures because we see the pattern lone pair adjacent to a pi bond. Now, assigning the hybridizations, I think nitrogen is the most straightforward. So there are 3 electron domains on nitrogen. So nitrogen is unambiguously sp2 hybridized. And in fact, there are 120-degree bond angles for nitrogen in nitrate. Now, if we're thinking about the oxygens, we might get different answers. But I am here to tell you that all 3 oxygens are sp2 hybridized. You might say, no, wait, what? No, how could that possibly be? For example, this hydrogen looks sp2 hybridized here, right? It has 1, 2, 3 domains of electrons. But it looks sp3 over here with 4 domains. So doesn't it switch back and forth, or what's going on here? No, it does not switch back and forth. We already know that that is not the right way to think about resonance structures. Nitrate is described by the 3 structures. It is all 3 at the same time all the time. So all the oxygens are sp2 hybridized because all 3 oxygen atoms make a pi bonding interaction with nitrogen at all times, even though it's not shown that way in the individual Lewis structures. Remember, Lewis structures are imperfect. What is necessary to make a pi bonding interaction? P orbitals are necessary to make pi bonding interactions. Do sp3 hybrid atoms have p orbitals? No, they do not. Thus, the oxygen atoms cannot be sp3 hybridized. They must be sp2 hybridized and have a p orbital to accommodate that pi bonding interaction that we see in these resonance structures for nitrate. So if on a test, because we care about that, right, I gave you nitrate and I pointed to this atom and I said, what is the hybridization? You would need to say sp2. You would need to recognize that nitrate is described by these 3 resonance structures, which show us that all 3 of those oxygen atoms make a pi bonding interaction with nitrogen, and the hybridization must accommodate this. In order to make a pi bonding interaction, the atom must have a p orbital, and thus must be sp2 hybridized. Here is the bottom line, the final word on resonance structures in an electronic structure, just meaning where the electrons are for a given molecule. And here I even have my little picture here that tells you how important it is. A given molecule has a single, only one electronic structure. Thus, it has only one geometry or hybridization at the atoms that make it up. The atoms are not switching back and forth between trigonal, planar, and tetrahedral. They have one single geometry. This means that a molecule is not, it is absolutely not switching back and forth between the resonance structures. It isn't, oh, now I'm this resonance structure, now this one, now this one. No, it is all of them at the same time. Sorry if I sound a little excited, but this is tough and I need you to get it. So I'm going to be excited and say it over and over again. The molecule is not switching back and forth between the resonance structure. The electrons are in all the places indicated by all of the resonance structures at all times. The real structure is a composite. It is a blend of the reasonable resonance structures. Just like we talked about for benzene, we said that benzene can be described by these 2 resonance structures. And so it is not alternating long and short bonds. It actually has 6 bonds of all the same length. Now we're seeing something very similar for nitrate. Nitrate is actually described by those 3 resonance structures, and that means that all of the oxygens must be sp2 hybridized, and guess what? All of the NO bonds have the same length as well. When we can show pi electrons or double bond electrons in multiple places when they're described by resonance structures, then we have what's called delocalized pi bonding. Which of these pictures better describes the pi bonding in the nitrate ion? Is it A or is it B? A certainly looks like one of the resonance structures. B looks like that composite. It really represents the real electronic structure, where all 3 atoms are making a pi bonding interaction with nitrogen all at the same time. This does not mean that nitrogen is making 3 full double bonds. No. Those electrons in the double bond are just spread out. Those 2 electrons in the double bond, let's point it out right here. These 2 electrons in the double bond, they're actually spread out between all 4 atoms at all times. And that's what's indicated by this structure, which represents the composite of all 3 resonance structures, represents the real electronic structure. Let's revisit our question from the beginning of class. What information must be included in a Lewis structure? Not much, really. It's the atoms and the valence electrons which make up the bonds and the lone pairs. What information might be missing from a Lewis structure? Well, certainly the shape, thus the hybridization. So we do need to count electron domains, think about shape, and also whether or not the molecule is described by resonance structures, which will affect what? Well, that will affect hybridization. We've just seen that. That will affect bond length. Is it a single bond? Is it a double bond? Etc. So we really have to think carefully when we look at a Lewis structure. Have we met the learning goals for today? Yes. We can identify the hybridization of an atom based on its electron pair geometry. Remember what we said at the very, very beginning, many minutes ago. Tetrahedral, sp3. Trigonoplanar, sp2. Linear, sp. Now, I do hope that you understood what the model of hybridization is and where it came from when I went through these examples. But ultimately, you need to know this master table in order to move on and to describe the bonding that occurs in organic compounds. Hybrid orbitals make sigma bonds and hold lone pairs. They put the domains in the observed spatial relationships. And leftover p orbitals make pi bonds, or you might encounter them as empty later on as we continue to look at more molecules. We can describe the types of bonds, sigma and pi, and the atomic orbitals used to make them for a given molecule. Hybrid orbitals make the sigma bonds, and p orbitals make pi bonds. Be able to draw pictures. Describe also means drawing the pictures like I was doing with you earlier. And then finally, you should apply the model of hybridization to molecules described by multiple resonance structures. That makes it harder, right? We looked at nitrate just now as an example. You should look at a different molecule. You should think about formamide. What's the hybridization of all the atoms in formamide? What are the bond angles? Finally, summarize and reflect. Do not skip this slide. And then once you've done that, ask me any questions that you have, and then it's time to practice.